Any question before we start? Alright, let's start beams. There are, as we talked on Monday class, there are different types of the beams. Something like this, which we call simply supported beam. It might be under concentrated load or distributed load, or another type of the beam is cantilever beam. In this course, what we are going to do, we are going to find the critical section first on the beam, and then suppose what would be the critical section? It's a section in which the failure likely occurs. So we would like to figure out at which position of this beam or that beam we are going to have the failure if it occurs. After we find that section, for example, this is the section, this is where which is representing critical section. Then I'm going to look at the cross section here, which is going to be something like this. And then I will find the critical point. Which point of that critical section is going to see the failure first if it occurs. So critical section, then critical point. So when you are given with the beam, we are just reviewing now the materials that we go further in deep in this topic. So when you are given with this beam or the other one, the first thing that you need to do is finding the reactions at supporting points. So the simply supported beam has two supporting points. We should find the reactions at that point. If you just think about this beam, which has been connected to this simply supported beam, if you apply a force somewhere, anywhere, you can imagine that it's going to start rotating about this point. So it tells me this pin or this supported point cannot support any moment. It's going to rotate about this pin. But here, when I'm looking at this beam, it's not going to move. So if it doesn't move, it means the bending moment or the moment about this point and this point, it's going to be 0. So this is one equation that I can use to find the reactions at two supporting points. So if I have something like this, F1, F2, F1 is located at the position of, at the distance of L1. The total length is L, and F2 is located at the distance of L2 from the starting point. So the reactions would be, I will label as R1 and R2. We would like to find R1 and R2. Summation of the force should be equals to 0 because this is not moving. It tells me R1 goes up minus F1, which goes down, minus F2 plus R2 should be equals to 0. This is the similar thing that you should do for any other beams, including cantilever or simple support. The second equation that I can write, if this is point A, this is point B, you can write either bending moment at point A or bending moment at point B equals to 0. Just use one of these equations. I'm using sigma m with respect to point A equals to 0. So what would be the external moment about point A? I apply force F1 at the distance of L1. Force times distance is making bending moment, or it's making the beam rotating in clockwise. Clockwise is negative, counterclockwise is positive. So the first one is negative F1 times the distance, which is L1. Second force has a distance of L2. It's still making clockwise rotation. And this reaction times the distance is making counterclockwise, which is positive. So plus R2 times F, set it equals to 0. So equation 1, equation 2. So two equations, two are unknown. R1 and R2 are unknown. I can find R2 from this equation, plug in there, and find R1. So this is the first step that we need to do for all beams, finding the reactions at the supporting point. For cantilever beam, it's a little bit different because in cantilever beam, the supporting point can support the moment. If you apply force with the distance from the supporting point, it's not going to rotate. So we have two equations. If I draw the free body diagram of the beam, here I have force F1 at the ending point, which is the supporting point. I'm going to have the reaction force and the reaction of the moment. Just write the same equation. Sigma F equals to 0. F1 goes down, negative F1, R1 goes up. So R1 equals to F1. You can find the reaction force simply by writing this equation. Second equation, bending moment should be equal to 0. On entire of the beam. So then this M is positive because it's making clockwise. Negative F1 times L1 is making rotation clockwise, which is negative. So you can find M equals to F1 times L1. So for cantilever beam, we have reaction force and reaction moment. In simply supported, we only have reaction forces. So before we go further, we need to do these steps. Good? You have seen this in mechanics of the material. Of course, we are just reviewing to make sure that you have fully understanding about the beam analysis. All right. After we find the R1 and R2 and R1 and M, due to the loading is gonna make internal force and internal moment. Internal force and internal load, internal moment. We call internal force shear force because it's a vertical load. It's a vertical load. It's making shear force, and internal moment we call it bending moment. So now imagine I'm gonna represent the internal force and internal moment. So if I cut the beam at the distance of x, I just cut the beam at the distance of x from point A, and I represent this here. Here I have R1. This is the only thing that I have at point A, and at the distance of x, at the section that I cut, I'm gonna have internal shear force. The downward is going to be positive for internal shear force. And also I'm going to have internal bending moment. This is how I represent the internal shear force and internal bending moment on a section that I cut. So I put the arrow such that it's making counterclockwise rotation. As you see, it's making counterclockwise. And put the arrow down for the shear force, because for the shear force, I consider the downward arrow as a positive. Then, for this section that I cut, I'm writing the same equation. R1, summation of the force should be equal to 0. Why? Because this section that I cut, it doesn't move. So it's going to be R1, which goes up, minus V equals to 0. So the shear force is going to be R1. I could find the value, the magnitude of the shear force. And summation of the moment should be 0 about point A. Because point A is not rotating, the summation of the moment about point A should be 0. What do we have? We have positive M because it's making counterclockwise rotation about point A. And this force times the distance from point A is making moment in opposite direction, which is clockwise. Negative V times X equals to 0. So M is going to be V times X. So moment, bending moment would be V times X, and V you could find up there, M would be R1 times X. So bending moment here is varying with the X in a linear relation. So first thing is find the reaction at the supporting point. The second thing that we need to do, we should figure out how many sections do we need to cut. How can I figure out the number of sections? You'll start from point A, you move to the right side. From point A up to the first force that you will see is going to be section 1. Then you pass the first force, you go to the next force, you call it section 2, and from this force to the end of the beam is going to be the section 3. So it means you need to cut the beam 3 times on section 1, section 2, and section 3. So for section 1, V is R times V is R1, and M is R1 times X, as I calculated that. Now for section 2, I cut it at the distance of X. This X is different than this. It's going to be from L1 up to L2. So if I cut it at X1, what I will get is something like this. R1, F1 at the distance of L1, and here I'm going to have positive V and positive F. And this distance is X. Make sense? I'm writing these two equations one more time. Summation of the F should be equal to 0. Positive R1 goes up, negative F1, negative V should be equal to 0. So I can find V equals to R1 minus F1. Summation of the moment at point A should be 0 because this point cannot rotate. This force times this distance, this force times this distance is making clockwise, which is negative. Negative F1 times L1. This V times the distance, which is X, is making negative rotation, and this moment is making positive because it's a counterclockwise. Set it equals to 0. Keep M in this side, move the other term to the left side. M would be positive F1 L1, positive V times X. Section 2. So this is how you can find shear force and the bending moment on section 2. We can plug in V by this one. I just saved the space, so I didn't plug in the corresponding equation. So now it's time to cut the section at section 3 with the distance of X on section 3. It's gonna be the same, just different value. R1, F1, F2, V, and M. This is L1, this is L2. Summation of the force equals to 0. Positive R1, negative F1, negative F2, negative V equals to 0. Find V. V equals to R1 minus F1 minus F2. Summation of the moment about point A equals to 0. This force times this distance, negative F1 times L1. This force times this distance is making clockwise. This force times this distance is making negative, and M is going to be positive. keep M this side, move the other terms to the other side. F1 L1 plus F2 L2 plus Vx. And that's all. These are shear force for section 1, section 2, and section 3, which covers entire of the beam, and these are the moment or bending moment for entire of the beam. So if you plot this graph, x-axis is representing the location of the beam. It's going to start from 0 up to L, which is the length of the beam. And here, the y-axis is representing the shear force. On section 1 means from 0 to L1, the shear force is going to be positive R1, just a straight line. It's going to represent the shear force on section 1, section 1. On section 2, the shear force is going to be R1 minus F1. Depending on the value of R1 and F1, you might get positive or negative value. If R1 is greater than F1, then you will get positive. If F1 is greater than R1, you will get negative. I'm just writing, I assume R1 is greater than R1 minus F1. So for section 2, you will get V like this. And for this one, you can draw the other one that you can see right here as a R1 minus F1 minus F2. So which is going to be section 3. We call this diagram a shear force diagram or SFD. In the beam chapter, we are representing with SFD, which representing the shear force over the beam. The other diagram that we will talk about that is gonna called bending moments diagram or BMD. X goes from 0 to L. Just draw this line. From 0 to L1, the moment diagram is going to look like this. 0 up the way to R1 times L1. X if you plug in L1. Here, you might get something like this. Which representing this equation for X between L1 to L2. And for the last one, it's going to look like this, which representing the bending moment on the section 3. So if you like to find shear force at any desired X, you are just look at the X, suppose here, and read the numbers. At this location, shear force is going to be R1. What would be the corresponding bending moment? Just read the value for bending moment. these two graphs is going to help us to find the critical section. Shear force is making shear stress. So shear force is providing the shear stress. And bending moment is making normal stress. So the higher value, the greater value for the shear force, the greater shear stress is gonna be experienced on the beam. So by looking at this, for the shear force, the critical section is gonna be at location L1 because the R1 is greater than these two. And for the bending moments, if I ask you what would be the critical section, this point L2 is gonna be the critical section for normal stress. On the beam, this is almost always true that for the critical section we look at the bending moment diagram because shear stress compared to the normal stresses is a small number. So what is making critical section is basically bending moment diagram. So where is at which section we are going to have the greatest moment. Any question on this? Before I go through one example, there is another thing that I should review from that course. V shear force, we can have this correlation between V and M. V is derivative of M or bending moment with respect to X. If I multiply both sides, V dx equals to dm. If I integrate suppose you have point C and D. Point C is here, you know where is the location of point C, and point D is there. Point D, location C, and location D. Here in this bending moment diagram, it's going to be here and right here. The moment at point C, the moment at point D. The difference between moment of these 2 points, MD minus MC, is going to be the area surrounded by shear force, the integration of V dx from point C to D. So if you calculate this area, whatever is this area, is going to give you the difference between moment of point D and C. Make sense? I know that you have covered them, but I just want to make sure that we review this material before we go to the stress analysis and design of the beams. Any question on this? Let me solve one example. if we have a simply supported beam with the length of 20 inch, force 200 is applied at the location of 4 inch, and force 100 applied at the middle of the beam, which is 10 inch from point A. We would like to draw the shear force diagram and bending moment diagram and find the critical section on this beam. After we find the critical section, we are doing the analysis, or if we need to design, we are doing the design for that section. So I'm just repeating again and again, because critical section is very important on analysis and design process. So again, first find R1 and R2, the reactions, the only reactions at point A and B. Point A and B cannot have moment as a reaction because they cannot support moment. So R1 is positive, R2 is positive, negative 200, negative 100 equals to 0. Summation of the force equals to 0. Summation of the moment at either point A or B. I'm writing for point A. Reaction R1 doesn't have any moment at this point because the distance is 0. Force times distance equals to 0. 200 times 4 is making clockwise. Clockwise is negative. Negative 200 times 4 is negative, minus 100 times 10. Another negative moment, but this R2 times 20 is making positive. Set it equals to 0. Two equation, two unknown. R2 is the only variable here. I can find R2. 90 is it pound? Yes, pound. The units are in US. It's pound. So R2 is 90. R1 plus R2 equals to 300. So R1 is 210 pounds. I could find R1 and R2. Then we should figure out how many sections do we need. You start from point A. Before you reach the first point, first force, you are gonna have first section. After the first force, you will see the second force. Just stop and label this as a second section. And the rest is gonna be section number 3. I should cut it 3 times. One here. R1, V, M at the distance of X, section 1. R1 goes up, minus V goes down, equals to 0. There is no other force on this section that I cut. So V would be R1, R1 is 210 pounds. For the moment, this doesn't have any moment at this point because the distance is 0. This V times this distance, the distance is X. Making clockwise, negative V times X plus M equals to 0. Then M would be Vx, which is 210 times X. This is the bending moment for this section. Now cut the section here, the beam at that location, R1, V, M, and don't forget this force, 200. Repeat the same things. R1 goes up, 200 goes down, the force pointing down. I have another force, negative V. No other force showing up here, so it's gonna be 0 at the right side. So I'm looking for V. V would be R1 minus 200. 210 minus 200 is gonna be 10. Bending moment equals to 0. I have two force making bending moment clockwise, these two, and one positive counterclockwise. Force times distance. The distance is 4 inch. Negative 200 times 4 plus negative V times X plus M equals to 0. Negative V times X plus M equals to 0. I'm looking for M. M would be 800 plus V times X. V is 10, 800 plus 10X. So I could find shear force, bending moment equation on the first two sections. Now I cut the section at location. I'm going to cut the beam at section 3. R1, this force, this 100 force, and internal force. 1, 2, 3, 4. 4 forces showing up. R1 is positive, 200 is negative, 100 is negative, and V is negative. Set it equals to 0. So V would be R1 minus 300. R1 is 210 minus 300 is going to be negative 90 pounds. Summation of the moment at position A should be set equals to 0. This 200, the distance is 4, and it's making negative rotation because it's a clockwise. This 100 times 10 inch is making clockwise, and this V times its distance from point A, which is X, plus M, set is equal to 0. So M would be 800 here, negative, 1000 there, negative 1800, plus V times X, and V was 90, negative 90. This equation, this shear force, and this bending moment are valid for any X between 0 and 4 inch. Because section 1 representing this part. Section 2 is valid for any X greater than 4 inch or equals to 4 inch and less than or equal to 10 inch. From here to here. And section 3 is valid for any x greater than 10 or equal to 10 and less than or equals to 20. As you see, I covered from 0 to 20, which is entire of the beam. Now I'm going to draw the shear force diagram and bending moment diagram. So for any x between 0 and 4, what would be the shear force? It's positive 210. If it's 210, just draw a straight horizontal line. From point 4 to point 10, we have positive 10. A straight line. And from point 10 up to point 20, I'm going to get the shear force of negative 90. This is the shear force diagram. If I ask you at which location we are going to have the critical section, if I'm just looking at the shear force, any section from 0 to 4, it's going to see the 210 pounds. So any section between 0 and 4 is going to be critical section if you only look at the shear force. Bending moment. From 0 to 4, the bending moment is 210 times x. M would be 210 times x. It's a straight line. At x equals to 0, moment is 0. At x equals to 4, it's going to be 840. It's going to look like this. Here. If I plug in 4 here, I should get the same moment that I got over there. There shouldn't be any discontinuity. At x equals to 4, m would be 800 plus 40, which is 840. It's going to start from this point. And at the end of the section, which is 10, 10 times 10 is going to be 100 plus 800 and 900. It's going to end up to this point. And last, 1800 minus 90x. At x equals to 10, which is the border of these two sections, you should get the same 900. As you see, 1800 minus 900, it's going to be positive 900. It's going to be this. And the last point, you should get 0 because at the ending point of the beam, it cannot have any bending moment. It cannot support any moment. We can check. 1800 minus 90 times 20 is going to be 1800 minus 1800. So it's going to be 0. And this is how you can check also your equation. Now, based on this bending moment diagram, if I ask you which section is going to be the critical section is going to be at x equals to 10 at the middle of the beam, based on this loading. We are going to do the design or analysis for that section because it's going to see the greatest moment. Any question on this? I just did the analysis from the scratch for beam. So for the homework, you know how to do that. So now, so for there is a toolbox on MATLAB. Let me just put that folder first. The name is BMD. Right here, bending moment diagram underline tool. So if you just type BMD underline tool and the resolutions. No, the problem is the resolution of, it doesn't like the resolution of, let me work on this tomorrow. So I will explain this example tomorrow on the BMD tool.